The purpose of this video is going to be to show you how to use a spreadsheet program to analyze data that Logger Pro gave us in the Angry Bird Lab. There's two purposes to this. One is that the data we get will allow us to develop our model for accelerated motion. But the other is that using a spreadsheet program is a really important thing to do. Almost every field uses this type of program to eliminate having to hand calculate large amounts of data. You can actually bulk calculate stuff and it makes life easier. So I think it's an essential skill to get before you leave high school. So let's look at how we use this program. I'm using the open source LibreOffice for this video because it's the easiest for me to make a screencast with, but many students will be using either Microsoft Excel or Google Sheets. Honestly, most spreadsheet programs work nearly identically. The one difference is how you make a graph. So I'm going to use this video to show essentially how you manipulate the data, and then I'll try to give suggestions on how to make a graph, and I can help you with that in class with your preferred spreadsheet. We are interested in motion up and down, which is along the y-axis. We're not interested right now in motion left and right, which is along the x-axis. So we don't need all this data here. If you can't read what the different column headings are, you can resize cells by grabbing the line between them and clicking and dragging. We do not need x position, and we do not need either of the velocities. So we just have position and y velocity. So go ahead and clear your cells. So a strange thing about our data is that our first time is not 0. This is actually the first time at which I clicked, but the 0 point for time, according to Logger Pro, is when the video started recording. So I really want this to be time 0. I can accomplish that by subtracting 2.463 from every data point to rescale my times. Now I could do that in a tedious way, but a spreadsheet makes it a lot easier. What we do is we type a formula. The spreadsheet knows it's a formula if you type the equal key. And once you do that, you can click on the thing you want to calculate. So in my case, it's time. And that enters the cell into a formula. I then can do minus 2.463. And I get an answer. So the magic of spreadsheet comes here. If we go back to the thing we just calculated, we can see it did a simple thing like a calculator would do. But it didn't enter the original number we were trying to subtract from. It entered the cell number. And what happens if I grab this little black box at the lower right corner, and I click it and I drag down? The spreadsheet actually goes ahead and does all the calculations for me. And if we click on one of these individual cells, we can see it change the cell number based on whatever row we're in. So you can get all your data calculated at once. What we want to do now is make a graph with time on the x-axis and position on the y-axis. This is going to be the one part of the process that is different between different versions of spreadsheet programs. I will have some common ones posted on the Flickr album so you can take a look at them. We'll just briefly look at a couple right now too. But ultimately, you got to figure out how your spreadsheet program makes this graph. Here in LibreOffice, you look for the button that says Insert Chart. Here in LibreOffice, you look for the button that says Insert Chart. In Google Sheets, it sometimes helps if you have your data in the order of what you want on the x-axis, then what you want on the y-axis, and then you highlight all that data. You then press the Insert Chart button, which looks like this. You may have to click more to find it. I think Excel's probably the easiest. Once you've got that chart set up, you just click Select Data. Then you can click on Add. And then you basically just highlight by clicking and dragging over everything you want on your x-axis. You have to do that first. Then you click here, delete what's in there, and drag over everything you want on your y-axis. At that point, you can hit OK. Google Sheets is sometimes kind of random over what it graphs. So if you look over here, you'll have a chance to change the type of chart. And also, as you select the data, you can click here and then click and drag across your times, which go on our x-axis. Google Sheets calls the y-axis series. So you can click here and edit and click and drag over your positions. You can then click here and click delete because you only want one data set on the graph. Once you've got the basic graph of your data, you're going to have to go exploring for options. And basically, you want to dress your graph up. You want to label your axes. You want to put the units on there. Just make your graph so that it's something presentable. This is going to be different in every spreadsheet program, and I think the best way to find these options is to just go exploring. Alright, so hopefully by this point you've played around with your program and you've graphed the data that you wanted, you've got everything labeled. At this point we want to add a trend line. This is again going to be slightly different between different spreadsheets. In Excel it's under Add Chart Element, Trend Line, and you want the More options so you have a lot of choices. In Google Sheets you can find it under the Customize tab. But in general, the process is to right-click the data and to choose Insert Trend Line. You're going to get a lot of options, and you can really fit any sort of function you want to that. But we're sort of predicting it's a parabola, and most spreadsheets call that a polynomial of degree 2. The other thing we want to get out of this program is we want to show the equation on the chart. So if we do those two things, we should end up getting our equation. And we do. A lot of times the formatting will be weird, so you just grab your equation and drag it so you can read it. And that's our equation for position. So our graph of vertical position versus time shows that as time passes, the slope is decreasing, decreases to 0, and then increases again, but in the opposite direction. This is going to give us an interesting velocity time graph, and I'd like to get that. It would be nice if we could find a function to calculate the slope at every point along here. That would be the most valid way to get a velocity function. That's actually what derivative calculus is, so you'll learn about that in a later math class. The best we can do here is we can just take the slope between consecutive data points. In other words, consecutive values of time and position. So here's the slope formula. And what we're going to try to do is plug into the spreadsheet to calculate this slope at every single point that we have position time data for. The formula looks kind of scary at first, but I hope you can see that it's the same as the slope formula. I've merely clicked on a cell that goes with y2 and y1, and one with t2 and t1. Let's see what that looks like live. So I've made a new column called velocity, and we're starting in the second data point row because we're going to do 0.2 minus 0.1, so we have to have a data point above us. To do any sort of calculation, you type equals. That tells the spreadsheet you want to put a formula in. We're going to put both the numerator and the denominator of the slope in parentheses, so we don't have any order of operation issues. So anyway, velocity is y2 minus y1. Well, this is y2. That's y1. We'll close that parentheses. And we're going to divide by, open parentheses again, t2 minus, oops, that's multiply, sorry, minus t1, close parentheses. So that'll be the velocity between those 2 points. We'll hit enter. And we'll click it and drag the formula down. So we've got all our velocities. And now we're going to make another graph of time versus velocity. We'll put it right next to this graph. So the data seems to show that for an object flying through the air, at least as far as vertical distance is concerned, we seem to have a parabolic position time graph. The slope got less and less and less as the Angry Bird came to the top. It was a zero slope at the top, and then it increased in the negative direction. That seems to have generated a linear velocity time graph. Our velocity is dropping until we stop, and it's increasing again, but in the opposite direction. So these are the kind of graphs we've played a little bit with in class, but now we actually have equations that can be fit to these graphs. Let's talk a little bit more about what these equations mean. So I think the velocity graph is easier to interpret being linear. The equation for a line is always y equals mx plus b. And let's just customize it for this graph. On the y-axis we had velocity, on the x-axis we had time. So we have velocity equals the slope times time. And we've said that the slope on a velocity time graph is this thing we call acceleration. So in other words, it's how fast velocity changes. The intercept is just what the velocity was at the beginning, VO. So we have this new equation, which we apparently can use for finding the velocity at different times when we have this type of force pulling on something. I think it's also kind of fascinating to look at the shape of this graph. It's linear, it has a constant slope, and that means the acceleration is constant. We've got about minus 10 as the slope of the velocity graph, so if we made an acceleration time graph, it would look like this. What's that practically mean? These velocities correspond to when the Angry Bird is on the way up. This corresponds when it's at its highest point, velocity is decreased to 0. It's slowing down here. These correspond to as it's getting faster and faster in the negative direction. But the striking thing is, slowing down, stopping, speeding up, the acceleration was the same throughout. It was getting 10 meters per second more negative as time passed. So we call that a constant acceleration. And it seems to happen when forces are constant in how hard they pull. This is going to be a really good model for how a lot of objects behave, because it turns out there are a lot of constant forces in the world. The last thing we're going to have to do is look at this equation. Translating it for this graph, it's y is minus 5-ish t squared plus 3-ish t plus that number. It'd be worth looking and seeing if any of those numbers duplicate between the graphs. We'll go into this equation a little bit in the next class.